First of all, I'd like to give thanks to the organization for giving me this opportunity to be here today with you. I'm very glad to be here today and have the opportunity to visit the NOR plant later. So I have prepared a short presentation to talk about R&D topics concerning solar thermal electricity plants. This presentation is divided into 3 sections. The first section is devoted to a very short introduction to remind you about solar thermal electricity plants and to explain why R&D is so important for these technologies nowadays. The second section is the main section of this presentation. It's fully devoted to explain those R&D topics that could be a more significant impact on the development of these technologies. And at the end of the presentation, I would like to give you just the conclusions, a short list of conclusions. So you all know that a solar thermal electricity plant is a system where solar energy is concentrated, converted into thermal energy, and then this thermal energy is used in a thermodynamic cycle to produce electricity. So a solar thermal electricity plant is basically an electricity plant where fossil fuels have been replaced by thermal energy delivered by concentrating solar thermal systems. At present, there are 4 technologies. We have central receiver plants. We have plants using parabolic-trough, Stirling dishes, and linear Fresnel concentrators. And now, very quickly, I will show you a picture of each of them. This is a nice view of a solar thermal electricity plant with central receiver. This is the technology that will be used in NOR 3 here in Ouarzazate. We have the receiver on top of the tower, and we have many mirrors called heliostats reflecting the solar radiation onto the receiver, and the working fluid in the receiver is heated up because of this concentrated solar radiation. And then we have a power block, a power conversion system at the bottom of the tower, converting this thermal energy into electricity. This is a typical view of a solar field with parabolic-trough collector. This is the technology you already have in NOR 1 and also in NOR 2. In a solar field with parabolic-trough collectors, we have many parallel rows of parabolic-trough collectors. You can see them here. And we have several collectors connected in series in every row. The parabolic troughs are concentrating the solar radiation onto the focal line. In the focal line, we have a receiver. Thermal oil is circulating inside the receiver, and the thermal oil is heated by this concentrated solar radiation. Another technology is the Stirling Dish technology. In this technology, the solar concentrator is a paraboloid of revolution. At the focal point of this concentrator, we have the absorber of a Stirling engine. In the Stirling engine, we have hydrogen or helium running inside, and this gas is heated in the absorber, which is located in the focal line of the concentrator. And the 4th technology is called linear Fresnel concentrators. In this technology, we have long reflectors with independent rotation axis, and each reflector is reflecting solar radiation onto the receiver tube, which is fixed. So the receiver tube does not move, it's fixed, and the mirrors are reflecting the solar radiation onto this receiver. Once again, the working fluid circulating inside the receiver is heated up because of this concentrated solar radiation. If we have a look at this map, we can see what we have now in the world. The green bars are the installed power already in operation with solar thermal electricity plants. In the blue bar, we have the projects under construction, project that will be in operation very soon. And with the yellow bar, we have the forecast for 2020. The NOR 1 plant is not yet included because it's not yet officially in operation in this green bar. But we can see that we already have 4 gigawatts of installed power all over the world, 4 gigawatts. This is not much if we compare this number with PV or with wind and other renewable energy, but 4 gigawatt is something. So we are growing up. So from this picture, we easily come to the conclusion that there is a significant commercial deployment. So there are many projects all over the world. And this commercial deployment is taking place in those countries with public incentives. Public incentives, feed-in tariff, tax credits, or something similar. Because the cost of electricity produced by solar thermal power plant is still higher than electricity produced with conventional systems. And therefore, we have to compensate this different cost with subsidies or with public help. It's also clear that these public incentives will be reduced in the next year, because these public incentives are only trying to help during the first stage of deployment. But after that, the public incentives are usually reduced, and therefore, we have to reduce also the cost of the electricity produced with this system, because otherwise we'll not be able to go into the market. And therefore, for me, it's very clear that a significant effort has to be devoted in order to reduce the cost of electricity produced by solar thermal electricity plants, because this is the only way to continue with the commercial deployment, and this is the only way to develop the learning curve of this technology. So this is the main reason why R&D is so important for these technologies nowadays, because this is the only way to improve the technology, to develop new components to reduce cost and increase the efficiency. And can we achieve a significant cost reduction? The answer is yes. We can achieve a cost reduction higher than 50%. There are several studies. Here you can see the result of the study performed by A.T. Kearney in 2011. And they came to the conclusion that more than 50% cost reduction, a cost reduction higher than 50% can be achieved by 2025. And this is not just, this is not just a guess. This is supported by a detailed study. So a detailed study showing how we can reduce cost of each component, how we can increase the efficiency, and so on. And the conclusion from that study was that we can achieve this cost reduction easily in 20 years, so by 2025. If we compare this cost reduction with the cost reduction already achieved by PV or wind, we see that this cost reduction is even lower than the cost reduction already achieved by PV and wind. Here you have a graphic showing the cost reduction achieved by PV and wind when the total installed power was 10 gigawatts. So in 2010, we already had 10 gigawatt worldwide of PV plants. And the cost reduction was 70% from 1988. Concerning wind energy, they achieved also 60% cost reduction between 1994 and 2010. So we see clearly that such a cost reduction is fully feasible, and other technologies have already achieved even higher cost reduction. So 50% cost reduction for solar thermal electricity plant is not a dream, it's fully feasible, and we can achieve it. But we need a significant effort on R&D in order to achieve such a cost reduction. What can we do? Or how can we classify the priority level of R&D topics? The priority level of R&D topic are given according to the two the contribution of that priority level to the main objectives of the solar thermal electricity sector. So at present, this sector has 4 main objectives. The more an R&D topic can contribute to any of them, the more important or the higher priority we give to that R&D subject. So our 4 main objectives at present are cost reduction, efficiency increase, better dispatchability. Dispatchability is the main benefit of this technology when we compare this technology with other renewable energies, for instance, PV or wind. And the 4th objective is better environmental sustainability, lower environmental footprint. So the higher the contribution to any of these objectives, the higher priority for that R&D topic. And these high priority topics have been already identified at the Spanish level. Solar Concentra is a public platform supported by the Spanish ministry. In this platform, universities are collaborating with industry and also with R&D groups in order to improve the technology. The result from this study can be found in this link with the priority R&D topics. And the priority R&D topics have already been defined by Stella. Stella is the European Solar Thermal Electricity Association. The scientific and technical committee of Stella published a report with the R&D topic with higher priorities. This report is available in this link. So if you want to get further information about the more important R&D topic, you can download this document. This is the front page of this document. And there is a detailed description of all the R&D topic that will help to achieve a significant cost reduction or better dispatchability or better efficiencies. And now I would like to explain with more details all these topics. The list is very long, but I will focus on those topics with a higher potential to contribute for this, to this cost reduction. How can we reduce the cost? By developing new concentrators, new heliostats, new Parabolic-Trough, new parabolic dishes, because now the models we have available for Parabolic-Trough or heliostat, the design currently available, require a lot of manpower for the assembly and for the manufacture. And the cost of this manpower is a significant portion of the overall cost of the system. If we have a look to this collector design, this is the collector design implemented in the first 3 Spanish plants. You can see the structure is a complex structure with many steel bars, and a lot of manpower is needed to manufacture and to assemble all these elements with a high accuracy. We even need a special assembling jig in order to connect all the elements of the structure with high accuracy. So it needs time, it needs a lot of manpower. So if we develop new design demanding less manpower, we can achieve a significant cost reduction. We have already improved the designs. Here you can see one of the Parabolic-Trough collectors we are using nowadays. If you compare this structure with that one, you easily understand that a significant cost reduction has been already achieved. But there is still a lot of room for further improvement concerning the design, the overall design of the concentrator in order to reduce the manpower cost, not only for the manufacturer, but also for the assembly on site. Because nowadays, the manpower for the assembly is still high. Something similar happens with the heliostat. Here you have a typical heliostat. This is a heliostat with 120 square meter of reflecting surface. You can see the structure. It's composed of many mirror facets or mirror elements. All these mirror elements must be assembled with a very, very high accuracy in order to be sure that the reflected sunlight is going into the receiver and is not lost. Nowadays, we have new designs, much more simple. You can see this structure is very simple, much more simple than this one. So we are improving the designs in order to reduce the cost, the manpower cost. And there is still a lot of room for further improvements with the development of new heliostat and new solar concentrators. Other R&D topic to reduce the cost is the design or the improvement of key components. For instance, the receivers, the receiver of parabolic trough. The receivers for parabolic trough collectors are expensive, very, very expensive, because the technical level of this component is very high. And there is one component in the receiver, which is the glass to metal sealing here, to connect the glass cover with vellows, stainless steel vellows. So this glass to metal sealing fails from time to time. And when it fails, we lose the vacuum and we have to replace the receiver tube. We have to replace the tube, we have to cut the tube, we have to drain the collector, cut the tube, and weld a new tube on the collector, and this is very, very expensive. So the improvement of this glass to metal welding will reduce significantly the maintenance cost of solar fields with parabolic trough collectors. Another key component are the ball joints. The ball joints are elements to allow the independent movement of adjacent collectors. So we need these elements. In these elements, we have a graphite packing inside in order to allow rotation of both sides. This graphite packing has to be replaced from time to time in order to avoid leaks. So it needs, let's say, a significant maintenance cost because we have thousands of these elements in a solar thermal power plant with parabolic trough collectors. Concerning Stirling dishes, nowadays this technology is not very successful. Why is not very successful? Because it's quite interesting. This is the technology with the highest efficiency when converting solar radiation into electricity. With this technology, with Stirling engines, we can convert solar radiation into electricity with a peak efficiency higher than 30%, and yearly efficiency higher than 25%, which is very high efficiency. However, the maintenance cost of the Stirling engine we have already available in the market, the maintenance costs are very high because inside the engine we have helium or hydrogen working at very high pressure, at a very high temperature, about 650 or 700 degrees C, and the pressure is above 150 bars. Due to this high temperature and high pressure, the components fail very often, and we have to replace the components. We have to dismantle the engine. We have to, so due to these maintenance problems, this technology is not very successful, and there is no big commercial plant at present using this technology. There are only prototypes. At the Plataforma Solar de Almería, the place where I'm working, we have 6 units, but we are aware that this technology has to be improved. So there is a significant room for improvement concerning the Stirling engine. The concentrators are okay. They are already at an affordable cost, but the Stirling engines must be improved in order to reduce the maintenance cost. What about efficiency? How can we improve the efficiency? Because if we improve the efficiency, the cost of electricity will be reduced. Well, we can increase the efficiency increasing the working temperature. If we increase the temperature at the receiver, we increase the efficiency of the thermodynamic cycle. You know, the higher the top temperature of a Rankine cycle, the higher the efficiency. And the same with a Brayton cycle. So if we can increase the temperature, the working temperature in the receiver, we would increase also the efficiency, the overall efficiency of the plant. And how can we increase the working temperature? We can increase the temperature, increasing the incident flux, increasing the solar radiation flux on the receiver. The higher the flux density on the receiver, the higher the temperature, and therefore the higher the overall efficiency of the plant. But we need new materials. You need new materials suitable for higher solar radiation fluxes. So we could achieve these densities, about 1 megawatt per square meter of concentrated solar radiation, if we want to increase the temperature. Now we are working below that level, but we need to achieve such a flux of solar concentration at the receiver. And for that, we need new materials suitable for higher temperatures with a high durability. Also, working fluids. You know that in Parabolic-Trough, the system, the plant NOR1, we are going to visit in a couple of hours. The working fluid in the Parabolic-Trough collector is thermal oil. This is the standard technology nowadays for Parabolic-Trough. Here you can see the typical simplified scheme of a solar thermal electricity plant with Parabolic-Trough collectors. In the solar field, we have thermal oil. The thermal oil is heated from 295 up to 395 because the thermal limit of this oil is 398. Above 398, there is a very strong, a very significant degradation of the oil. And we have to replace a significant amount of oil every year. So this is the reason why we cannot work at temperatures higher than 395, because the thermal limit of the oil is avoiding higher temperatures. So this hot oil is then sent to either the power block to produce steam in the steam generator, or it's also sent to the thermal storage system. This is the thermal storage system that Professor Basin has already shown in the previous talk with a hot and cold tank. So this is the technology we have nowadays for Parabolic-Trough collectors. And we have this limit imposed by the thermal oil, because the thermal oil currently available cannot work at high temperature. So if we develop new working fluids suitable for higher temperature, then the efficiency of the thermodynamic cycle and the efficiency of the overall plant would be higher. So this is why at present we have different candidates. One candidate to increase the temperature for Parabolic-Trough is direct steam generation. With direct steam generation, we put liquid water at the inlet of the solar field, and this liquid water is converted into saturated or superheated steam as it circulates through the solar field. So at the inlet of the solar field, we have liquid water, and at the outlet of the solar field, we have superheated steam. So at the PSA in Spain, we have producing superheated steam at 100 bar and 450 degrees C since 5 years ago. So the technology is ready, but the main problem for the commercial deployment of this technology is the lack of a suitable thermal storage system, because we need a phase change material. So we need thermal storage based on PCMs. The technology already explained by Professor Bassin in the previous talk. And such a technology is not yet fully commercially available. So it's not, there are some prototypes and there is a lot of research concerning development of phase change materials, but we cannot, we cannot install direct steam generating plants with parabolic trough with thermal storage until we have not developed such a storage. Because the sensible heat storage with molten salt is not suitable for direct steam generation. So this is the main barrier for the commercial implementation of direct steam generation. But the technology for the solar field, the technology to produce high pressure and high temperature steam directly in the receiver tubes of the parabolic trough is already available. The technology is already available, and there is no problem to increase the temperature at the outlet of the solar field, because there is no thermal limit for the steam. There is a thermal limit, a clear thermal limit for the thermal oil, but such a thermal limit does not exist for the steam. Supercritical CO2 is also a good option, it's a promising option to increase the temperature, because there is no problem to work with CO2, carbon dioxide, at 700 or even 800 degrees C in tower systems. So this is why in USA, supercritical CO2 is considered a very, very promising option to increase the temperature in solar thermal power plants with central receiver technology. Also, the development of new salt mixture, because at present we are using what we call solar salt. Solar salt is a mixture, 60% of sodium nitrates and 40% of potassium nitrates. This is what we are using nowadays, but the maximum working temperature for this mixture is 600 degrees, because above 600 degrees, the nitrates are converted into nitrates, and the corrosion increases significantly. So we have to develop, we have to find new molten salt with new components. There are many R&D groups also working in this subject, because if we develop cheap molten salt for higher temperature, we could achieve higher temperatures in the solar field, in the solar receivers. Another very interesting R&D topic is the development of new turbo machinery. It means steam turbines for solar thermal power plant, because the power equipment we are using now, the power equipment installed in Nord 1 and installed in the Spanish plant. In Spain, we have 50 solar thermal power plant with a total installed power of 2.3 gigawatt. And the power system, the steam turbines in all those plants are conventional. I mean, they have not been developed especially for this application. So we are using a standard equipment, and because of that, the efficiency is not as high, is not so high as it could be. So nowadays in Europe, there is an association of turbine manufacturers willing to develop new turbines, especially designed for solar thermal power plant, because with new designs, they can easily increase by 3 points the overall efficiency of the plant. Such an efficiency increase is a lot. So 3%, not 3%, 3 points from 38 to 41% efficiency is a lot. And that would be a significant help to reduce the cost of the electricity produced with this system. What about dispatchability? You know, dispatchability is associated with thermal storage, because dispatchability is the capability to produce electricity when solar radiation is not available. And the only way to do that is using thermal storage. So how can we improve the dispatchability? Well, one option is by improving the current thermal storage system with molten salt. You have already seen this picture in the previous talk. This is a typical molten salt thermal storage system with sensible heat. We have a cold tank and hot tank and heat exchanger to transfer, to exchange thermal energy from the thermal oil to the molten salt and from the molten salt to the thermal oil during the charging on the charging process. So nowadays, this is the system we have available. This system is quite good. The efficiency of the storage is about 93% from charging to discharging, so only thermal losses about 7%, which is a very, very small amount. But we can also improve significantly this system. How? First of all, improving the salts. Improving the salts because the molten salt we are using now are not, let's say, perfect from a thermal standpoint. I mean, the thermal conductivity is very low, very, very low. The heat capacity is reasonable, but we can improve the thermal conduction and also the heat capacity using nanoparticles. With nanoparticles, we can double the thermal conductivity of the molten salt. In Spain, there are R&D groups already investigating this subject, and they have improved significantly the thermal conductivity and the heat capacity of the molten salt with nanoparticles of silica. So with a very small amount of nanoparticles, you can significantly increase the thermal conductivity and the heat capacity of the molten salt, which is a very important improvement in order to increase the efficiency. So nanoparticles is a very, very interesting subject to improve also this, the technology of solar thermal power plants. Also, developing new salt mixture in order to increase the temperature of the thermal storage system. I have already explained that. If we develop new fluids, not only for the solar field, but also for the thermal storage, we can increase the efficiency of the overall plant. A very interesting topic is the possibility to store energy with solid media, pebbles or byproducts from the steel industry. So these elements are these solid media are very, very cheap, and it could be a very good option for thermal storage with sensible heat. So far, we are using molten salt. So we increase the temperature of the molten salt from 290 to 400 or 450 or 500, depending on the technology, Parabolic-Trough or central receiver system. But with solid storage media, we could also do that with a very cheap product or very cheap storage media. So this is also a very interesting R&D topic to improve the dispatchability of the solar thermal power plants. Also, the development of phase change material. I will not spend time on this because Professor Bassin has already talked about that in the previous talk. Phase change materials is a very, very interesting topic. And this is a topic very suitable for a small R&D group. You don't need, let's say, large test facilities, outdoor facilities, so you can investigate on phase change material in laboratories, in a small test facilities. Some prototypes have been already tested. Here you can see 2 prototypes tested in Spain with phase change material. The capacity of this prototype was 200 kilowatt-hour, and the capacity of this one was 700 kilowatt-hour. But we need bigger capacities because in Spain the solar thermal power plants we are now running in Spain, the power unit is 50 megawatt. So typical plant in Spain is 50 megawatt unit power. And the thermal storage capacity is 1 gigawatt hour. 1 gigawatt hour thermal storage. So with this capacity, we can run the power block at full power for 7.5 hours. So this is the reason why at night, solar thermal power plants in Spain are delivering electricity to the grid, because they have 40% of the Spanish plant, not 100%, but 40% of the plants are provided with a thermal storage system. And this thermal storage system allows the plant to deliver electricity at night when the solar radiation is not. But the capacity of such a system is very large. It's 1 gigawatt hour. So we need a significant step forward in order to go from, let's say, 1 megawatt hour to 1 gigawatt hour. So the systems we have already developed for phase change materials are feasible for a small capacity. Sometimes we develop something that is very good for a small capacity, but it's not feasible at all for large capacity. This is also something we have to keep in mind. Something that is feasible for a small capacity may be not feasible for very large capacities. Thermochemical storage. Professor Bassin has already explained it, so I will not spend time on that. This is very promising and very interesting because of the very high energy density. This is the main benefit, the high density, energy density of this system. However, I think this R&D topic is a long-term research. So we must be aware that this is very interesting, but we shouldn't expect significant results in a very short term, because there are significant technical challenge. So we are progressing, but we cannot expect that large commercial systems using thermochemical storage will be available tomorrow. So we still have to work for, let's say, many years in order to have this technology fully available commercially. Concerning the environmental footprint, this is also very important because the solar thermal power plants we are using nowadays are consuming a lot of water in the cooling system of the power block. So we have to condense the steam coming from the steam turbine. And from this cooling system, we need water. And a significant amount of water is evaporated in the cooling system. We evaporate approximately 3.5 liters of water per kilowatt hour of electricity. This is a rough number. It depends from one plant to another, but a rough number is 3.5 liters of water per kilowatt hour. So if a 50 megawatt plant in Spain is producing 140 gigawatt hour of electricity per year, you can calculate how many thousands of cubic meters of water are evaporated in the cooling system. So you know that water is usually not available in arid places. So we have to reduce this environmental footprint, this environmental impact. How? Reducing the water consumption. How can we reduce the water consumption? Well, improving dry cooling system, because nowadays we already have dry cooling system. In Abu Dhabi, there is a solar thermal power plant with a unit power of 100 megawatt, and the cooling system of that plant is dry cooling. They are using dry cooling, so the technology is already available. The only problem is that the efficiency of the plant, when we replace wet cooling by dry cooling, is about 3% lower. And the investment cost for a dry cooling system is higher than for a wet cooling system. This is the main reason why, if you have available water, you prefer wet cooling system, because the investment cost is lower and the efficiency is a bit higher. But the dry cooling systems we have available nowadays can be improved. In fact, they have been already improved for the last 3-4 years. And the efficiency of the dry cooling system has been improved significantly for the last 3-4 years. They have improved the heat transfer in the heat exchangers. So now the temperature gradient between the ambient temperature and the steam temperature inside the heat exchangers has been reduced. And therefore, the efficiency has been increased. So there is a lot of potential improvements concerning the dry cooling system. We can also install hybrid cooling system. This is also very, very interesting, because with a hybrid cooling system, we reduce only 1% the efficiency, but we reduce 50% the water consumption. In a hybrid cooling system, we have a dry cooling for winter time, because in winter time, the ambient temperature is lower, and we use a wet cooling system for summertime, when the ambient temperature is higher and the efficiency of the dry cooling system would be lower. So with such a hybrid concept, we reduce a little the efficiency of the overall plant, but we reduce significantly the water consumption, about 50%. So this is also a very, very promising option. And we have also what we call negative thermal storage. What's negative thermal storage? Well, negative thermal storage could be a very, very, very good option for desertic areas where the overnight temperatures are very low and the temperature during sunlight hours are very high. Because we could store the cold temperatures at night, cooling down a media, and this cold media can be used during solar time to condense the steam coming out from the turbine. So we store cold energy at night to use it for the cooling system during sunlight hours. So we would have, in those plants, we would have 2 storage systems. One storage system to take cold temperatures at night, and a second storage system to store thermal energy from the solar field. Do you understand the conceptual idea behind this concept of negative thermal storage? This is feasible only for those places where the overnight temperature are much lower than the ambient temperature during sunlight hours, which is very usual in desertic areas. And once again, developing new working fluids to replace thermal oils, because the thermal oils we are using in parabolic-trough collectors are contaminant, are pollutant. So when we have a leak, if we have a leak in the solar field, we contaminate the soil, the ground, and we have to remove this contamination, and this is very, very expensive. So we have to find new working fluids with a lower environmental impact, because oil is good enough. This is why we are using today oil, but it's not the perfect choice, because it's pollutant, it's contaminant. There is also fire hazards in the solar field, because when there is a leak of oil at high temperature, we get a fire in the solar field. So we should try to replace thermal oil by another fluids with lower environmental impact. And finally, let me give 2 conclusions to summarize the presentation. First of all, the high priority R&D topics have been identified at the Spanish and European level, and this, let's say, this analysis is also valid for any other countries. So you can get this list of high priority R&D topics from the website of Stella, the European Solar Thermal Electricity Association. And secondly, and this is very important, there are so many R&D topics that there is room for everybody. There is room for chemists, physicists, engineers, equipment manufacturers. So there are so many things we can do to improve the technology, to reduce the cost, to increase the efficiency, to reduce the environmental impact, and so on. There are so many things that there is room for everybody. For small R&D groups, for large R&D groups, for industry, for everybody. And encourage everybody willing to participate in this effort to join the international team. Nowadays, there are thousands of people working on all these topics. 10 years ago, the group was very, very small. But nowadays, there are many R&D groups working on these topics in order to improve the technology of solar thermal electricity plants. And well, this is all what I wanted to show you. And now I would be glad to answer your questions if you have any questions. Thank you very much for your attention.